there are some main steps that you can see here that have been done on research in powder. There's the bottom's noted who notice the first theories of frictional forces. Another major point in research is actually Charles Park standardized empirical methods like tap density, current, and sense-off. Further than communicate a translational shear tester, which is used for generally silent design, motor design, which is actually the focus of the information. And now it's 3 years, I have part around the power cell embedded, which is further a step in this power research. Depending on what you're doing with your powders, you're going to have quite a lot of different issues and challenges that you might be facing. So if you're having a silo, you might be wondering, okay, how do I have to design the silos that have workflow or mass flow? If you're using additives, you might want to know, okay, how will the additive influence the processing happening? Because it can be good in one step, but it might be causing problems in other steps. So basically, the goal is to have measurement methods that can help you study the powder, understand your powder, in any step of the process. Because the silo is like that reactor. There are quite a lot of different influences in powders. Basically, you can roughly qualify that into internal influences, so internal influences in the sense of what the particles look like, what does the bulk look like, what's the size or the size distribution of the particles, because there's already influence behavior. And then of course there are external influences like the humidity, the temperature, the normal stress conditions of the powder.
You are talking about humidity, that is the external humidity I was talking about, because particles or powders sometimes have inherent moisture, which is absorbed moisture. So are those two different or they are the same one you're talking about? Because heating will occur even on the moisture content of the powder.
It's yeah, you're right. Action should be written in the internal influences as well, because of course the humidity, the inherent humidity of a sample will change its cohesiveness. But of course, if it's very humid in the environment, the powders might hold this humidity and might get moist as well and increase.
So moisture content and external humidity.
Yes. So when we look at a few of these influences, a major point is the load condition. So basically, under which stress the powder is, okay, the granular medium is. One example, we're in the very high loads, you can see on the left with silos. Another one would be for tableting, for compacting the samples. And then when we move further to the right, we get to lower loads and to aerated or deaerated samples, which means the powder is just a set of free. And then finally, in a fluidized state, where powder is either fluidized to liquid similar state by passing air through it, or actually just by letting it fall through gravity. It's already fluidizing the powder. So what is influenced? What are the characteristics, or what is the behaviors that are influenced by these internal and external influences? Will be the powder flow, of course. The fluidization characteristics might change depending on what you're doing with your sample, permeability, and so on. We'll see all these factors in more detail a bit later. One question that's probably one of the most important is the powder flow. Actually, this comes afterwards, okay. So let's talk about the cohesiveness before. Secretiveness basically is one of the factors that will also determine the powder flow. It's very cohesive powders will not flow well. They will fluidize badly. For example, if we try to fluidize it, passing air through it, there will be channels in this sample. If these powders are non-cohesive or free-flowing, it will fluidize easily and will generally flow better. So when we go from this to the flow behavior, that's definitely the case, is that it's always difficult to predict flow behavior. It's not something that can be predicted theoretically by running simulations, at least not easily. Can be done, or it's being studied, but there are so many influences and parameters that have to be taken into account that theoretical simulations get very large. So what is basically necessary are reliable and reproducible measurement methods to understand the power and to be able to predict its behavior during the processing of the counting. So for this, there are first off some empirical measurements that have been done for quite a while. These measurements are actually very similar to classical traditional rheology. This is what has been done before rheometers were used. In traditional rheology, a liquid was put into a funnel, the funnel was open, and the time was measured for the liquid to drop. And that is exactly what is done also with powder. So for example, Hall flow meters was used for this. But going from the Hall flow meter to a flowability value can be complicated because the main influence in this funnel will be actually the friction between the particles and the raw material, and less actually the flow properties of the sample. So I know we're working with the university in Austria, who's working a lot in additive manufacturing of metals. And they, for example, they say, okay, this is a standardized method because everybody uses it, but it actually doesn't say anything about the flowability, because one powder will not actually flow through the Hall flow meter, will be stuck inside, and they're going to have to start tapping it or stirring it or whatever. And it will be actually very nice flowing in the process. So the question is, does this correspond to your process and how you're handling the samples or not? Another method which is used quite commonly is tapping. So this is either done manually or with a tapping device. You fill the powder into a tube, you tap it 200 times, and you measure the volume before and after the tapping, and this will be an indication of how the powder flows. Again, this is an indication, it's not a very precise value, and it can give you a comparable value between powders. So one issue with these empirical measurements actually is mainly that the reproducibility depends quite strongly on the operator. So for example, if you're doing this funnel measurement, this really depends on how you're preparing the funnel, how you're loading the funnel. So if you put in the powder from very high, you're going to have some pre-compaction of the powder, which will then hinder the outflow and then change the time that is needed, that the powder needs to flow out of the funnel. So a goal when you're looking at these measurement methods is to always avoid operator influence, or to find a way to prepare the samples to reduce operator influence. So from these these empirical methods, there are improvements that have been developed. Quite a lot of them are available commercially, and some of them are just too scientific because it's just simple. So there are a few different cohesion tests, for example, or a spring tester. There are penetration tests where a sample is compacted and then a tip is pushed into the sample and the normal force is measured. Or there's uniaxial testing, which is similar to a certain extent to shear testing, actually. There's also wall friction testing, fluidization tests, and powder rheology, which actually includes a number of these tests, these advanced methods, and then also some of the empirical methods that we saw before in a, let's say, improved way, at least, a more controlled measurement way. So one thing that I'd just like to point out is shear cell, which is one of the most common methods of studying powders, which works very well for adhesive powders, and where you're looking at powders under high load. So if you're designing a silo or a hopper, then the shear cell